All right, so actually, I'm going to start out with describing. So we left off last class talking about how we can do multiple linear regression where we've got not just one variable on that right-hand side, we're trying to estimate the relationship between that X and Y variable, but we can control for a lot of other factors. So I'm going to start out with an example today, and it'll be kind of comprehensive. So we'll use several regressions, just get more interpretations. I'll be reiterating some of the things I talked about last week. There's really not a ton of new stuff, a couple little wrinkles in what we've been doing, but really it's going to be just going over more and more examples. We're using p-values to make rejection decisions. We're interpreting coefficients, looking at the R squared, et cetera. So the first example is going to be sports related, but we'll kind of quickly turn it into not sports related, right? And hopefully by the time we work through the entire thing, we'll see like we've used several regressions to make kind of more optimal decisions for the future. So the first regression that we're going to think about, though, we're going to look at is whether or not a basketball team in the NCAA makes it into that first round of the NCAA men's basketball tournament. So 1 if they did, 0 if they did. And one thing that an athletic department might be interested in is, well, how can I impact whether or not I make it into that first round by how much I'm spending on that program, right? So our X variable here is going to be the number of dollars spent on the men's basketball program. Our dependent variable, we didn't have any examples like this last week, is just going to be a 1, 0. So 1 if they made it into that first round, 0 if they did. So usually the way that we interpret this slope coefficient is we say it's the effect of, the predicted change from, EF. Oh, no, I crossed this out. Sorry. I started writing something and I decided to change. So the predicted change from a 1 unit increase in the X variable that we see in the Y variable, right? So we can kind of phrase this several different ways. We could say, it's the effect of a 1 unit change in our X variable on the predicted value of our Y variable, or the predicted change from a 1 unit increase in the X variable that we would see in the Y variable, right? Or thinking about it as if that X variable goes up by 1 unit, that slope coefficient is how much we expect the Y variable to change by, okay? Now, when our Y variable, our dependent variable is 1, 0, it gets a little bit weird because like last class, we're saying, okay, if the SAT score goes up by 1, 1 point, that coefficient was how much we expected the GPA to increase by, and kind of GPA is measured in this nice continuous way. We don't have a continuous variable here. So our coefficients are going to represent moving from 0 to 1 or changes in the probability that this Y variable is equal to 1. So the way that we would interpret this variable is the effect of what's 1 unit? That would be $1, right? So the effect of a $1 increase in men's basketball expenses on the probability Y is equal to 1, or that they make that first round of the tournament. Okay? So now it's like the units before, like when we had the GPA, the units was just the number of points. If I had salary, it'd be the number of dollars, or predicted dollar increase or decrease. But when I have a 1, 0 variable for that dependent variable, the coefficient represents a change in the probability that we move from that 0 to the 1 group. Remember, we looked at variables on the right-hand side, and then we said, okay, the 1 unit change would be going from the 0 to the 1 group. Well, now that coefficient is saying, okay, what's the change in the probability of moving from that 0 to the 1 group? Any questions on that before we keep moving? So it's a little bit different, and I won't actually give you examples on the exam where I make the Y variable a 1, 0. I might use examples where we kind of like we did last week, where that X variable could be a 1, 0, and then the 1 unit change is just going from the 0 to the 1 group. But I think this is a pretty interesting example. It also kind of leads us up into an explanation where I can go through what I think is a really relevant and really interesting example next class. But that's how it would change our interpretation just a little bit, right? Because the units isn't going to be dollars, it's not going to be inches, it's not going to be whatever. Now the units of our y variable is like going from 0 to 1 or changes in the probability. Okay. So if I'm thinking about the sign of this slope coefficient, once I run this regression in Excel, what do you think the sign of this coefficient would be? If a university spends more money on their basketball program, what do you think happens to their chances they make it into this huge NCAA tournament? Probably positive, right? It probably goes up. Okay. So we think, okay, it's probably, once we see this estimate, probably positive. What do you think is going to be true about the size or the magnitude of that effect? Remember, the coefficient measures the effect of one unit, which here, one additional dollar. So what do you think is probably true about the size of this effect? If Ball State puts one more dollar into their basketball program, what do you think happens to their chances they make the tournament? Hardly goes up, right? We think it's positive, but the units are really small. Just like if we're thinking of like salary, like $1 isn't that much, right? And so we said last class, well, if I have the effect of one additional dollars, how can I get the effect of 1,000 additional dollars? Yeah, just multiply that by 1,000, right? Just like we did the SAT, we had the effect of 1 point. How do I get the effect of 100? Well, multiply that by 100, right? Just scale it up. So we'll do that here in a little bit once we get this estimate. But we also talked about, so we've got this, this regression we're interested in. We already talked about this. But we have to remember, this is very naive. There's probably a lot of other factors other than how much money they're spending on their basketball program that might impact whether or not they make it into the tournament. Right? What's the quality of the players on their team? Like, what's the size of the university? Right? And so if we leave out these other important variables, we said we're going to have this bias component in our estimate. Well, how can I get rid of that? Start including those important omitted variables, right? So just one of them I had thought about to make this point would be, let's throw in the number of undergraduates, right? So somehow we're controlling for the size of the university, but that's what that total undergraduate would be kind of a good measure of. So now the interpretation of my slope coefficient is the effect of one additional dollar spent on the predicted change in the probability I make it into that first round of the tournament, holding constant the total number of undergraduates. Well, that's a little more powerful statement, right? Two universities with the same number of undergraduates, but one of them spends an additional dollar on their basketball program. What's the change in the probability they make the tournament? So ignore this. This is kind of pushing it a little bit further than what I want to push you guys this semester. So I just have that in an old slide, and I want to kind of keep this example. So we'll just look at the actual regression output. So here's that first naive regression. Now, some of the things we talked about last week, my R squared, that's the proportion of the variation in my Y variable, or think about it as I'm explaining about 17% of the variation in that Y variable of whether or not they make it into the first round of the tournament by simply including how much money they're spending on the program. And the proportion of 0.17 would be I'm explaining 17%, right? We can just move the decimal 2 places to convert that proportion to a percentage. We also, just to kind of confirm our suspicions, this is positive. And I'm not showing you Excel output here, which I'll go through an Excel example at the end of the class. And that's how I'll kind of, that's what I'll show you on the exam is only Excel output. But we can see it, other statistical programs, they're going to be a little bit different looking, but it still tells us all the same things, right? We've got our R squared here, number of observations, our slope coefficients, standard errors, test statistics, p-values, our intercept or the constant. So it looks a little bit different format, but it's giving us all the same information. And sure enough, we found a positive but very small coefficient, right? E to the -8, so 0.70 and then an 8, right? Very, very small effect, which makes sense. It's $1, right? We'll talk a little bit more about scaling that here in a second. And then as I added in this additional control, what should happen to my R squared? Well, if I'm using more variables, right, to explain that Y variable, it should go up, right? And it does, right? Not by much, but it does go up a little bit. Right? So once I control for the total number of undergraduates, notice my coefficient does change a little bit. Not a whole lot, but right, I went from like 7 zeros and an 8 to 7 zeros and a 7. So a little bit smaller. Still significant, right? We've got p-value of 0. And when I say it's still significant, what am I referring to? So we said that when we run these regressions and we look at these slope coefficients, we always start out assuming that the slope coefficient is equal to 0, that there's no relationship between our x and our y variable. Or said differently, right? We're trying to find in our alternative hypothesis, is there an effect, right? Is that slope anything other than 0? So just like all of our hypothesis testing, we can compare our p-value to whatever alpha corresponds to the confidence level we want to either reject the null at. If this holds, we said we can reject the null, which rejecting the null here, if I reject that there's no relationship, what I'm really saying is I found evidence that there is a relationship. So saying that something is significant means that we can reject the null, or we're really saying that there's a significant relationship, right? So that's why we kind of use those significance levels of 10, 5, and 1%, which we said kind of correspond to the confidence levels of 99, 95, and 90%. So, it's hypothesis testing, but we get to skip a lot of the steps, right? We're going like right to the p-value right away, okay? Any questions on that before we keep moving here? There we go. So another thing that I had said we had talked about last class was we can use our regression output to make predictions, right? So if I want to predict whether or not a team makes it, into that first round of the tournament, I can use the output that I see from Excel or these other statistical programs. So we're going to use the less naive regression where we included the undergraduates as an additional control. So I get what? Put this up here. So this was 0.70, right, times kind of whatever the basketball expenses were. The other coefficients, what, 0.50, and then 422 times the total number of undergraduates, right? So all I was doing there, like I would have kind of my regression equation. I just plugged in those values that I had for the coefficients on those variables. Now, what's one thing I forgot here? I always have to add my intercept in, right? So I should have started with it. I was kind of didn't start with it to make a point, right? I need to add it in, which it's a negative value here. So what, 0.00966. Okay. So now if I wanted to, I can come up with predictions for hypothetical schools. Now I could use actual schools, like what their actual expenses and undergraduates are, but I could also do hypotheticals. So I could come up with the predictive probability, right, of making it into that first round. So maybe they spent, I don't know, $2 million on their basketball program and they had 1,500 undergraduates. Well, once I plug in those hypothetical X values, now it's just a pretty simple equation, right? We kind of last class looked at it in Excel where I had all my coefficients, all the hypothetical X values, just multiplied each coefficient by that variable's X value, and then added them all up. And don't forget the intercept, okay? So on that 5th Excel assignment, if you do choose to do it, and like I said, even if you don't do that for a grade, like because I dropped the lowest, I would look at that as like an additional practice for the exam, but you wouldn't want to forget to add your intercept in there when you're making predictions for that Y variable, okay? Any questions on this before we keep going here? Just starting to make a little bit of sense. Some people think that this linear regression stuff's like easier than the hypothesis testing and things like that. But anyways, we'll keep moving. So we've got these predictions we can make. There's one thing that we talked about last week that I didn't quite go over with multiple linear regression, although it's not much harder. So we said, how do I interpret my intercept? We said one way you can think about it is it's the expected value of y, or the predicted value of y, if my x variable is equal to 0, right? Because if my x variable is 0, 0 times anything is 0, I'm just left with the intercept. When we have multiple variables, the only thing that changes is it's when all the X variables are equal to 0, right? So now the interpretation of my intercept is if all the variables I've included on that right-hand side are equal to 0, the intercept is the predicted value of my Y variable. Right? So it's just instead of one variable being equal to 0, it's if all of them are equal to 0. So here I've got kind of a weird one, right? Because the interpretation would be if a team spends $0 on their basketball program and has 0 undergraduates, here's their predicted probability of making a tournament. And it's negative, which, doesn't make any sense, right? We can have negative probabilities, but the reason why is because remember what we were doing with a simple linear regression, I drew it out. We've got this line of best fit. That's really what we're estimating that slope of. And then that line has to start somewhere. That was our estimate for the intercept. We're doing the same thing when we include several other regressions or several other control variables into our regression. It's just that now instead of a line with a point where it starts on the y-axis, it's a 3-dimensional line where it's got a point where it starts on the y and z axis. And if I include 3 variables, it's this 4-dimensional point that I can't really visualize. And so anytime I have more than 3 variables, we couldn't even really draw this. You have to visualize matrix algebra, which I can't do. Some people are freak geniuses and really good at doing that. But that is the idea. It's like this starting point. If all the X variables are equal to 0, and then as the X values start to deviate, you start seeing this prediction, the predicted value of Y move all around. Okay. So you will have some weird interpretations sometimes for the intercept. And that's because we don't see any data points where we have 0 undergraduates, right? Or 0, well, maybe 0 expensive if they didn't have a program, but we wouldn't see 0 undergraduates. So it's kind of like this hypothetical starting point that we just can't see, but it has to start somewhere, right? That line does have to start somewhere. Okay. So interpretation of the intercept, kind of got that out of the way. And then we can start to move to, okay, I've got the effect of $1 additional. Or $1 additional. Sorry, I keep saying dollars there. So $1 additional. Well, how do I get the effect of $1 million additional spent? We'll just multiply it by 1 million. So we're going to go through some hypothetical thought experiments. So I think the average was about 1.4 million that these schools in the data set were spending on their basketball program. But there's a huge range, right? 7,000 to 23 million, right? Pretty big variance there, right? Standard deviation of 1.8 million. Okay. So I'm just going to look at the teams in the top 100 in terms of the schools that spent the most. Top 100 schools that spent the most. There, if they increase their budget by 10%, the average school must have been spending what? Just under $10 million in the top 100 schools there. So a 10% budget increase would be $935,000 additional dollars spent. So if I know the effect of $1 additional, the effect of this 10% budget increase would just be the effect of $1 times $935,000. So if a school in this top 100 increased their budget on average by 10% or $935,000, so this is like one, if you think about this, like one school, they increase their budget by $935,000 or their expenses, they would increase their probability of making it into the tournament by 0.069 or 6.9%. So decent effect there, right? But it is $1 million, or just under $1 million. But there's a lot of additional revenue. I forget. I think each school gets paid. I think the conference always gets 1.5 million, and then each additional school is 1.25, and then they get like 250,000 per win or something. So there, it's like, yeah, it's been $1 million, but the conference gets paid back by the NCAA pretty quickly for that. So we have a little bit more work to do to see if it's justified, but we're not trying to do that here. We're just trying to look at the effect of spending that additional money. You could do this for other schools like IU. Their 10% budget increase would be 1.2 million. So they increase the probability a little bit more. Ball State, a 10% increase. Well, they're not spending near as much. So their 10% more, their expenses will only be 150,000. So they could only increase their probably making the tournament by about 0.01. Okay. So you could do this for any school or a hypothetical school. If what if there was a school that spent $10 million on there? What would the change be? So you could do any different hypothetical amount. So we found a positive effect, and these aren't trivial changes in the probability. But I want to make another point here. We haven't controlled for a lot of other factors, right? And so what are some other things that we might want to control for that might be important omitted variables? Because I think we're still at like an R squared of 0.18, right? Yeah, there's still 82% of the variation that we're not explaining. Okay. So I had a couple ideas, and not just ideas, but things that I had in the data. So I wanted to somehow control for like, well, what's the quality of this program, right? And not necessarily in the current year, because I know how much I spend this year would impact the quality. So I'm going to look at like, well, what was the team's previous number of wins the year before? And did they make the tournament the previous year as well? I also thought about, well, what teams can spend more money? Teams that have larger fan bases, who are getting more ticket revenue in larger conferences. So I'm going to control for their revenues as well. If they have more money, they can spend it. Right? I then also did something that is a little bit further than what I'll expect from you. So I wouldn't throw something like this on an exam, but I wanted to kind of use some examples today to point out the strength or the power of regression. So here, what I did was I had a year variable in the data, but I wanted to make sure that, okay, it may not be that like things are on a linear trend. So I just wanted to include indicator or dummy variables for each year. So I created this variable in Excel, which was the observation from 2010? If it was, put a 1. If not, put a 0. Then another indicator variable. Was the observation from 2011? 1 if it was, 0 if it wasn't. I did that for every single year in the data. And then that should capture any effect of rule changes in any one year, maybe economic changes in the nation in any one of those years, right? So it kind of captures anything that would impact the probability of making the tournament that would kind of be impacting every team equally across those years. So just additional controls there. So I'm going to throw all of these into my regression on the right-hand side. And not surprisingly, my R squared goes up, right? Now it's still only at about 30%, right? Or just under 30%. So we still have a lot left that we might be concerned we're omitting some important variables. But now if we go to that men's basketball team expenses, now the effect of an additional $1 on the probability of making the tournament went from 7 zeros and a 7 to 7 zeros and a 2. So it's like quite a bit smaller, right? A third to a fourth of the size that it was before we controlled for all these additional factors. So as we include more controls and we get that R squared closer to 1, we're less concerned that we're omitting important variables. And the closer to a causal relationship, this slope coefficient will be. Now, it's still just evidence of a correlation, and it's evidence of a correlation holding constant a lot of other factors. So that's good, but there still could be some omitted variables that, we're leaving out here that might be really important and might be causing a slight bias in this estimate. But it's more reliable than our naive regressions, okay? If we look at the p-value here, it's 0.001. So we could say that what levels could we reject the null at here? What alphas is this p-value gonna be less than of our 3 benchmark? So less than 0.1? Yeah, it's less than 0.1, 0.05, 0.01. So we can reject the null at every significance level or at every confidence level, right? So with 99% confidence, I could say that I'm rejecting the null of no relationship, or I found pretty significant evidence there is a relationship between the amount of money spent in the program and whether or not they make it into that tournament. And it's even more powerful because it's like saying holding everything else constant. So the thought experiment there is 2 schools that either both made the tournament the prior year or they didn't, both have the same total number of undergraduates, both had the same exact revenues, both had the same number of wins the prior year, and we're looking at both those schools in the same time period, but one of them spends an additional $1 in their basketball program. What would the change in their probability of making the tournament be? That's a lot more powerful of a statement than what we were doing with our more naive regressions. Okay. Any questions on this before we kind of keep moving here? So I said to start out, going to be kind of more of a sports related example. You could do the exact same thing here and just replace your Y variable with did they win the NCAA tournament? So not only can you see, well, how does spending more money impact my probability of making the tournament? How does it impact the probability of winning the tournament? And you can go through the exact same kind of thought experiment. I had all those other controls too. I just didn't write it out because the equation would then going off the screen. And there we get much smaller effects, right? I think, 0.003 is a probability, or about a 0.39% increase in the probability you win the national championship from an additional $1 million spent, right? So yeah, it's still a positive impact, but it's a really low change in the percent that I'm going to win the national championship. I had to spend an additional $1 million to do it. So this is kind of more of the stuff that's related to kind of the sports side of it. Well, it's kind of interesting, and I'm not I didn't come up with this, but people have been thinking about this for a while. I just had some data where I could come up with an estimate for it. So the NCAA tournament, if you aren't aware, is this huge basketball tournament, right? It wasn't too long ago now, a couple months ago, and it generates a ton of money, right? Not only in kind of the ads that are sold for the games, the amount, gambling money on it, like we're talking, like, I'm guessing, I don't know the number off the top of my head, I'm guessing it's in the billions. I mean, it has definitely in the millions, if not, I'm sure with online betting now, it's definitely over $1 billion. So there's a lot of money involved, right? It's this huge, big event. A lot of people watch it. Even people who don't care about sports might fill out an office pool, and they might see the names on that list. Well, it's basically then advertising, right? Because I advertise why? Well, one of the main reasons is to make people aware that my product exists, right? And so here I would explain it the way to think about this is, if someone in California has no idea that Valparaiso University even exists, right? You may, because you might be from Indiana and maybe you've heard of it. Someone in California probably has no idea it exists, potentially, until they see, oh, maybe Valpo makes the NCAA tournament one year, and now they see it on the bracket. Oh, maybe they Google it up. I didn't know this was a university, or, Wichita State, or Robert Morris, like all these universities I never knew existed until you see them pop up on one of these NCAA brackets. So they're getting their name out there. People are aware of it. Maybe someone looks up the university. They find, oh, they got this really good program. Oh my, I didn't know it was like this history or whatever. So maybe they get more eyes. Maybe they get a couple more applications, right? Not everyone that sees the name is even going to Google the name, but there may be an incremental amount of people that do. So maybe we see that when a team makes it into that NCAA tournament, maybe it has an impact on the number of applications they receive, right? And we'll have to look at the previous year, right? Because the number of applications wouldn't come in until the following year. So if I make the tournament in the previous year, right, this is just a 1-0 variable. So our 1 unit change would be going from the 0 to the 1 group. So not making the tournament in the previous year to making the tournament in the previous year, the expected change in applications would be whatever estimate we see from Excel. Okay. So the effect of a 1 unit change, or going from not making the tournament to making the tournament, the predicted change in our Y variable of applications will be whatever that estimate we see for the slope coefficient. So if my story holds, this should be positive. Now, if I run a very naive regression, this looks like the effect is, if I make the tournament the previous year, I get 7,000 additional applications. This is wild, right? Well, I haven't control for anything, right? And what schools are more likely to make the tournament the previous year? Probably schools that are larger, or typically do year after year, or have, spend more money on their or on their program. So there's probably some things I want to control for. So one thing that would be really nice to control a lot of times is if you've got a dependent variable, controlling for what the value of that dependent variable was the year before will often be a really good control. So here, I'm going to add in this additional control of, well, how many applications did they get the prior year, right? So now it's like saying 2 schools controlling for the other factors. So 2 schools that got the same number of applications the year prior, or in the previous year, but one of them makes the tournament, right? The additional change in applications will be whatever our coefficient is. So now holding constant the number of applications they got the prior year, this is going to be a lot closer to the causal relationship as opposed to just a correlation. Now I said closer to, it won't be causal, but it will be closer to it. So we'll look at what happens. So when we only had that previous tournament variable, we're explaining what? The proportion of the variation in applications we were explaining was 0.07 or 7%. Okay. When I include the number of previous applications, my R-squared goes up to 0.97. I'm explaining 97% of the variation. The difference between those two was the impact of that previous applications variable, right? So if I reran this with only previous applications, it would have an R-squared of what, right around 0.9. So it's a really important control variable, right? And that kind of makes sense. Like you want to make sure you're looking at schools that like the previous applications they were getting, that kind of captures the effect of like everything that goes into applications, right? Now it's lagged one time period, but and things change over time, but not a ton, right? So having that previous measure of that dependent variable, the previous applications, is a really strong control here. And we don't have to be near as concerned about omitted variable, right? Or omitted variable bias, right? Because there's only 3% about the variation we can't explain. So now when we look at that previous tournament variable, holding constant the previous number of applications, now making the tournament in the prior year only increases applications by about 100 students. This seems more realistic, right? It seems like we're probably closer to the causal relationship. Now the p-value is 0.13 here. So what levels could I reject the null at? What alpha values is this going to be less than? Or 3 benchmark? None of them, right? So I can't quite say it has a significant relationship, although the p-value is 0.135. That's pretty close to 0.1. This isn't like we found absolutely no evidence. In fact, if I really wanted to, at the 85% confidence level, my alpha would be 0.15, and I actually could reject the null. So, what's the difference between the 85 and 90%? There's a difference. It's better to be able to say it with 90%, but 85 isn't nothing, right? So we still found evidence that there's a positive effect here. I then did an additional thing where, just like the year indicators, I created a indicator for what state the university was in. So we know there's probably differences across state. Different states have, economic factors that are impacted by it. And so the number of applications they receive might change as a result of that. So I can control for what state the university is in as well. If I do that, notice now I get a similar estimate. It's a little bit higher, but the p-value's fallen quite a bit, right? So now I can say 2 universities in the same state, same number of previous applications, but one of them makes the tournament, the other didn't. The expected or predicted change in my Y variable of applications would be about 167 additional students. And it's significant at what levels? My p-value is 0.017. So I can reject the null, which is that there's no relationship at what levels here? It's 0.017 less than an alpha of 0.1. Yeah. So I can reject the null at the 10% significance level or with 90% confidence. Is it less than 0.05? Yeah. So I can reject at the 5% significance level or with 95% confidence. Is it less than 0.01? No. So I failed to reject, or I can't say there's a significant relationship at that 99% confidence level. Okay. Any other questions before we keep moving here? Let me check where we're at on time. So I can't see that clock. I've ran into you guys about the clocks already. Yeah, it annoys me all semester. So one other thing that's kind of interesting, and I'll kind of just go through this pretty quickly because I didn't throw as many controls in here, but there is some research out there that shows this as well. So if I get more applications, which is what it looked like from the previous regression, if I accept the same number of students, what am I likely to do? Probably pick more students from the right side of like the quality distribution, right? Or try to accept what I think are going to be higher quality or higher performing students. So some data that exists out there for these universities is their 75th percentile math and English scores on the ACT. So I just use those as my dependent variables and said, okay, does making the tournament the previous year have a positive impact on this quality measure of my incoming freshman class? Okay? And what we see is p-value of 0, so we can reject the null, or there is a relationship between making the tournament and this 75th percentile ACT of the incoming freshman class. And it looks like it's positive. So it looks like these schools, when they make that tournament, can be a little bit pickier, and the quality of their incoming freshman class is a little bit higher. Doesn't matter if we use math or English, we kind of find similar effects. And like I said, there is some research out there that shows this. So, this is more like a comprehensive thing. Like we can start out the universities. Well, we want to spend more money on our basketball program. That's going to impact the athletic department. Maybe it's more likely to make the tournament. Okay, we get some money from making the tournament. That's great. But there's some of these indirect effects as well, right? Making the tournament is going to potentially get more people to be aware our university exists, or maybe just Google the university, see more of the programs. Maybe announcers talk about the schools during the games. And so we actually see an increase in the quality of the incoming freshman class as kind of a result of, we see a higher number of applications as well to these schools. Okay. So this is like in a university decision-making context for whether or not they should spend more money on their basketball program. Well, this could be, what if I spend more on R&D? How does that impact my probability of coming up with new patents? And then how does having new patents impact my revenue stream, right? So it would change the regressions and the variables we're using, but the same sort of thing could apply in a lot of different contexts, right? So we can use several regressions to understand like a larger problem, right? Or a larger question. We've talked through a lot of these things. So we did R squared, thinking about rejecting the null with our p-values, interpreting coefficients here, interpreting the coefficient on the intercept. But I think it's a nice kind of comprehensive example. It's at least hopefully somewhat interesting. And this is actual data. It's not like I made this up. Any questions before we move on? I want to show you some stuff in Excel here before we leave today. Okay. So I've got some other stuff in here. We'll pick up on this next class. If you go to that in-class data folder on Canvas, I put this COVID regression data up there. I'm going to open this up. And there's an issue that exists in this data set that I forgot that existed. So instead of acting, I don't know, surprised, I'll kind of show you this. So if we tried to run this regression here, one of these variables has some missing values. Well, if it's missing values, it can't run a regression with no number there. So it yells at you. It gives you like I think it says a lin-est error or something like that. So we'll clean this up here before we get started. So I have this data set. There was a bunch of different counties. I had the number of new cases of COVID that they had, I think back in, I was looking at like November or October of 2021. So last fall. I then had the population of the county, what region of the country they were in. So this is just a 1-0 variable if they were considered to be in the South or the Midwest, et cetera. I have the median household income of the county, whether or not the county was considered to be in a metro area or not. So that was just a 1-0 variable. The unemployment rate of the county, and then the percent of the county that was vaccinated up to that month, right? I think, like I said, I think it was October 21. I had some of this down here, so I believe I was pulling it off of this variable, October 2021. Yeah, so it would have been the difference in cases. So if we see these filters up here, if you go to this unemployment variable, I had an issue with it. So it shows me all the values, but if I scroll down, it had some blanks. Well, I can't run a regression with a blank value. So I'm going to deselect everything at the top and then have it only show me these blank observations. Oh, okay, so it was 5 counties in Alaska that probably don't report their unemployment. It's probably difficult for them to report unemployment data, or maybe there's just a lot of self-sustained individuals. And so, whatever, that the Bureau of Labor didn't have an unemployment percent for them. So I'm just going to select these 5 rows by kind of left clicking them, right, selecting them. And I'm just going to get rid of them. I can't use them. They're missing data that I needed. And then I'm going to go back to my unemployment variable, have it show me all the data again. Okay. So that was the issue that existed that we just kind of cleaned up. So you go to that unemployment variable, deselect everything. And then at the bottom, you had those blanks. Make sure you click that so it shows you the blanks, delete those rows, then go back and have it show you all the data again. And now we should be good to go. So the idea here is going to be, I'm looking at the number of new COVID cases. And what I was kind of interested in, what impacts it is the percent of the county that's vaccinated. Now, I had a bunch of additional controls as well, but we're really going to kind of focus on this slope coefficient. So how would I interpret this slope coefficient? The units of my X variable are just the percent, right? So a 1% increase in the vaccinated population causes my predicted Y variable, so the predicted number of new cases, to go up or down by, or to change by whatever that slope coefficient I find from Excel is. Now, what do you think is probably the sign of this slope coefficient? If 1% more of the county is vaccinated, what would you expect to happen to the number of new cases? You expect it would be negative. Right? So we're going to run this regression, see if that's true. I mean, we might not have a perfect, we might be capturing the causal relationship. It's still just a correlation, but we've got quite a few controls in there. So we should hopefully get a somewhat good R squared. So we'll go up here just as a reminder, File, Options, or on Mac, you go up to the Tools kind of bar at the top, go to your add-ins, and make sure that you have this analysis tool pack selected. Once you add it in once, it should always be there on the right-hand side under that data tab. So do you have a Mac? So you should go up to the tools. So you should see something a little bit different. It'll have like a box, and there, I think it's about halfway down. You should see something that says like add-ins, right? Or Excel add-ins. You want to make sure you find this analysis tool pack and make sure that's the one that's selected. And then it should pop up under your data tab. Did I get it to work? Talk to me after class and I'll try to help you. I don't know why it's giving that error. So we have this data under the data tab. We go over to data analysis. We have this regression tool at the very bottom. So I just scroll down, regression, hit OK. My Y variable we said was that number of new cases. Okay, so I'm just going to Control Shift or Command Shift on a Mac, hit the down arrow. That should select that number of new cases variable for me as my Y variable. And then go to my X variables. I can scroll up to the top and then select those. Also remember, if it doesn't send you automatically to the top, if you can remember what columns they're in, I said you can actually do this from the bottom as well. So I could select, I kind of remembered what columns those were in, Control Shift or Command Shift on Mac, hit the up arrow. Now it selects that entire range that way as well. So you can scroll all the way up if it makes it easier for you, but you can do that shortcut of, if it's a big data set like this, kind of just try to remember what columns are in, and you can select it up from the bottom. So I've got every variable from population to the % vaccinated selected. I've got the labels or the names selected as well, so I need to make sure that is checked off. Now I'm going to run this regression, and there's going to be one issue with it. So it's something that's kind of outside of the scope of this class, and I could have fixed it, but I want to show it to you just in case, I don't know, if you're doing something outside this class, you recognize it. So when I have all these indicators for what area of the country that the county was in, that included every, like I made like every state has to belong to at least one of those. Well, the problem is then what's the zero group? I need a control group. So the effect of being in the South relative to what? There's no control group. So I have to leave out one of those regions. Now, if I run this where I've included every region, Excel will drop one of them for me, right? But in practice, I should leave one of them out manually myself, but I'll just show you what happens. Excel will do it for us, not a big deal. So we hit OK. Notice it kicks out that Pacific region, right? Because it recognizes, well, I need a control group here for the region variable. So I'm going to zoom in a little bit here so we can see this. So if we look at our R squared, okay, we're up to about 0.82. So we're explaining about 82% of the variation in the number of new COVID cases. So this should be pretty reliable, or at least closer to a causal relationship than a very naive regression. So we'll scroll down here, got our coefficients, and here's our % vaccinated variable. So the interpretation of this coefficient is holding everything else constant. So two counties with the same population, same region of the country, right? They're both either in the South, Midwest, whatever. They both have the same household income, median income. They both are either in a metro area or they're not. They both have the same unemployment rate, but one of them has a 1 unit increase in this X variable, or is 1% more of their population vaccinated, the number of new additional cases is actually 17 people. Right? So not only do we not find a negative effect here, it's positive, and the p-value is less than all of our alphas. So we're rejecting that there's no relationship. Instead, we found evidence that there's a positive relationship here. Right? So this seems kind of weird. When I originally grabbed this data, I was like, oh yeah, I'll show them that when these counties are getting more people vaccinated, the number of cases are going down, right? But in fact, we find a positive effect here. So this is where two things. One, okay, there's still 18% of the variation we can't explain, right? Our R-squared was 0.82 about. So maybe we've omitted an important variable. And the variable we've probably omitted, we can kind of think through, maybe we're actually capturing something else with that percent vaccinated variable. So if more people are getting vaccinated, what do you think those people might be more likely to have done? Let's say you had someone who was like deathly afraid of COVID, and then they think the vaccine is 100% effective, they get the vaccine. What might they have been doing before that they no longer will? Staying in their home, wearing a mask, right? And so when you see a higher percent of the population getting vaccinated, it's likely that, well, you're also going to see their behaviors change. And if their behaviors change, if the vaccine isn't 100% effective, some of them will get COVID, right? And so if you see these huge changes in behaviors because people are getting vaccinated, that would be why that percent vaccinated variable looks like it's having a positive effect. It's not causal, it's just correlated with. So a really nice control would be like, I don't know, the number of customers served at a restaurant in that county, or the average number, or the number of people who, or maybe you looked at controlled for PPE sales, right? If you see fewer masks being purchased. Yeah.
What was the X and Y range?
Yep. So when I had that original data, we're going to that data analysis. I had that new cases selected as my Y variable. And then for my X variable, I just went population all the way over to this percent vaccinated. I didn't use this cases per person, as I just had that in the data. You could use that as your Y variable, and it just makes the interpretation a little bit harder. And then control shift, command shift on a Mac, hit the down arrow, make sure our labels are selected, and that should get us that same output. Any questions over anything I kind of mentioned there? So just walking through more examples, thinking about making these rejection decisions, interpreting the coefficient, maybe scaling the coefficient up like we did in the other example. Maybe I want the effect of getting 10% more of my population vaccinated. I'll just take this and multiply by 10. So we'll go through another example on Wednesday where we look at some traffic stop data and then kind of the officers and the driver's race and be able to estimate, like, is there differences in the probability that person gets a ticket or arrested, et cetera. So that's kind of an interesting result. So we'll go through that example on Wednesday. And then I'll probably start actually going through some of those exam review questions, just the linear regression ones, or add questions into those practice exams on Wednesday to think about, well, what is it going to look like on the exam when I'm asking you about these linear regression examples? Okay. All right. So you've got that fourth Connect in Excel. We're due at the end of the day today. Once those get turned in, I'll get those factored in the grade. I'm going to put up an online quiz that's due before we start class Wednesday. It'll be the very last one. And then once that due date is passed, I'll get those factored into the grades and drop those kind of 3 lowest like the syllabus states as well. Okay. All right. I'll see you guys on Wednesday.